Well, hello, everybody. I assume you can hear me. Yes. So thank you all for coming for this morning session. And we're going to be started off by Igor Pak, who is going to be talking about combinatorial interpretations. Igor, the floor is yours.
Thank you. Thank you, Bruce. And thank you, Vic. I'll wait for a few seconds and for the people to come in and just feel with my gratitude to the organizers and thank you. I actually don't see them. There's way too many people, but thank you all for having me. I'm very humbled to be here, and this place always felt like home, and it was home for a while. So I'm always glad to be back. All right. So my talk is going to be a little unusual. You can hear me? Yes? Okay, good. I'm going to talk about, so I changed the title a little just to make it in the form of a question. And I'm going to have a lot of questions during my talk. And the plan is to have about 4 deep questions. The idea is to basically discuss what is the real meaning of combinatorial interpretation and tell you about my recent work on the subject, but also put the whole thing into perspective from computational point of view. So here is the first question. The first question is, why do we care about combinatorial interpretation? Most of you already have an answer to that, but I'm just going to give my own version, which you may disagree with. And it's totally fine if you disagree with anything I'm going to say. That's totally fine, especially for graduate students. You should. Okay. I agree with your disagreement. So the second question I'm going to ask is, why are people so positive about existence of combinatorial interpretation? We've seen a lot of talks discussing, oh, it would be nice to have a combinatorial interpretation for this and for that. And we will hear for the rest of the week a few more talks about that. But should we really be so positive about that? Maybe we shouldn't. So the third thing I'm going to discuss is, what are the combinatorial interpretation? Do we even understand what that means? Okay, that's going to be very hard. This is the hardest part of the talk. What is the red word? The last part of the word is the new stuff I've been doing. And in fact, we can prove that some of them don't exist. And I'll tell you a little bit about that. But most of the talk is actually not going to be technical. I'm just going to show a lot of pictures and, hopefully we'll have a good time. Everyone okay? You all got the pictures? Yes? Okay. Okay, let's proceed. So this is just me telling you where to look for if you want to know more for the technical stuff. And as some of the speakers mentioned before, one of the key references that we have is Richard Stanley's paper about positivity in algebraic combinatorics. And he asks, this is me answering the first question. He asks several things that he really wants to find combinatorial interpretations for, and some of these are, most of these are not his problems. These are quite old problem. Kronecker coefficient is my favorite. I'm not going to define it. You've seen it before, and it was actually defined before. Greta talked about it quite a bit. So this number G lambda mu are going to come up over and over. Okay. That's the first combinatorial interpretation we want. The second is going to be about plethysm. I'm not going to say much of anything at all about that. So Anne Schilling is going to talk about that later this week. And those are, again, wonderful non-negative integers which do not have a combinatorial interpretation at the moment. And the third one, Schubert coefficient. So you'll hear a talk about that right after this talk. Sami is going to talk about it, if I understand correctly. Maybe I don't. Well, she is nodding her head in a strange direction. So I don't know. But if she doesn't, somebody else will, I'm sure. So those are 3 most wanted combinatorial interpretations. And if you're falling asleep completely and you're about to just close your eyes, the punchline of the talk is I question whether they do exist. Okay, I don't believe that. Everyone got that? Okay, don't fall asleep. There is more coming. So here is the second question. Why should people work on combinatorial interpretation? Because that's not a completely mathematical question. There are both mathematical and non-mathematical aspects to that. People do lots of things for a variety of reasons. Some of them are really strange reasons, and some of them are not. So here are the three non-mathematical reasons. I really favor the first one. The first one is a very good reason. And the second one, I followed religiously, if I may. That was important when I was a postdoc. And I don't like the third reason at all. And that's what I'm going to question. This is what I'm going to have real objections with. Okay, everyone got that? So, so here are some mathematical reasons for that. If this is not me believing, this is what I learned by asking sort of prompting questions to various people. And what they say is it would be great to have a combinatorial interpretation. You ask why, and they're like, well, we can do so much. We can get estimates for those numbers that I just showed you. Indeed, if they're counting some objects, then you can get some estimates for the number of those objects by using the nature of this combinatorial interpretation. Not always true, but when it works, it's fantastic. And I've done it before. It works really well sometimes. There are results of the saturation type problems. So this is appealing to other talks again. Littlewood-Richardson coefficients, famously by the Knudsen-Tau theorem, have a saturation result, and it's a wonderful thing to have. And the only way to get that, as far as we know, as far as I know, there are probably other proofs by now, is by using combinatorial interpretation, explicit combinatorial interpretation for Littlewood-Richardson coefficients. And once you have it, you can exploit it and obtain these remarkable results. And the last one is about vanishing problem. Vanishing problem is basically deciding whether the number is 0 or not. Okay. So if you know what your numbers are counting, then you can say, well, the number is 0 if there are no such objects. Okay, and that allows you to give a characterization for this for the parameters. And my general feeling is that's not these are wonderful things if that works, but they're not really how do I put it? They're not really powerful points in the case when we know so little. So I'm going to just give some examples, some of that Greta mentioned before. So if you start looking at estimates, it's just impossible to do anything with Kronecker coefficients. They're horrendously complicated. So here are best estimates that we know for, I don't know if you can see my mouse. These are the best estimates for the Kronecker coefficient of 3 staircases. That's a very nice, elementary, elegant Kronecker coefficient. The lower bound is 1. This is by Besson-Rotten bands, and the upper bound is the dimension. Okay, that's huge. That's square root of n factorial. There's a lot of room in between. And I've tried personally, failed. I cannot do anything. I've written a whole bunch of papers where I get estimates for Kronecker coefficients. I cannot do anything about that one. Okay. So if you believe there is a very nice, elegant combinatorial interpretation for Kronecker coefficients, maybe just try this one. Okay, what does it do in this case? Because I bet the right answer is closer to the top than the bottom. Okay, we just lower bounds are just really hard to do. Everyone with me? Okay, so second struggles, saturation struggles. In fact, saturation just fails for Kronecker coefficient. This is entirely obvious to anyone who just tries the first few examples. There is no reason to give saturation as an argument for having combinatorial interpretation because it's just wrong. Which sort of, if you put it differently, suggests that there is not going to be a really nice combinatorial interpretation for Kronecker coefficient, because if it was, maybe it would satisfy saturation, but there is no saturation. And moreover, a couple of years ago, in the very beginning of the whole COVID disaster, we proved with Greta that reduced Kronecker coefficients don't have saturation. That was conjectured for about 15 years ago. I think Greta mentioned it during question time, which sort of further pushes the point. I don't think even reduced Kronecker coefficients are going to have a combinatorial interpretation. But what do I know? You with me? Yeah. Any questions about anything? Am I too pushy? You can ask me questions. Okay. Well, if it's all clear, let me just mention that for Kronecker coefficients, deciding whether Kronecker coefficients are positive is just as hard as deciding if a graph has a Hamiltonian cycle. I mean, let me translate, really hard. So you should not, even if the input is in unary, which is what strongly means here. So you should not expect anything nice in that direction, is it? Okay, that's a beautiful result by Ikenmeyer, Müller, and Walter.
Do you expect to be at P complete, or you think it might even be harder?
This is what the whole talk is about. So wait, so the question was if I expect this to be NP complete or NP hard. And that's equivalent to asking if Kronecker coefficients are in NP. And I'll discuss a lot of that. So why would people believe that they exist? So I'll give you my personal opinion about other people's opinion. So take it with as much grain of salt as you can. And so there are two reasons, and one of them is positive experience. They study previous combinatorial interpretations and they love them. Who doesn't like Young's rule? Everyone does. That's what we learn in the beginning of studies of algebraic combinatorics. That's what we teach when we get to teach algebraic combinatorics, the first thing. And in fact, I recommend Bruce's book. So the second thing we learn, and this became maybe a month later, we learn how to do Littlewood-Richardson rule, and that's a beautiful combinatorial interpretation. Both very old, very classical. Who doesn't like those? Okay, so people have positive experience. They want to repeat them. They want to come back to their young days over and over again. Another beautiful combinatorial interpretation is pipe dreams. This is for Schubert polynomials. And it's much more recent, but it's just as beautiful. Once you see it, it's gorgeous. You want to do it more. Okay, you have a good experience. You want to repeat it. And in 4, I put everything else. There's a lot of stuff I'm not saying, and that's really, I apologize to all the authors of various extensions, generalizations, variations. This talk would not, the list wouldn't fit this talk. There's just a lot of stuff, but the top 3 are, in my opinion, perhaps the most remarkable ones. So, so here is the second reason why people continue doing combinatorial interpretation, again, in my personal opinion, and that is perseverance and optimism. So people, when people learn some stuff, they want to continue doing that stuff. Okay, it's a little strange to me because I actually enjoy learning and doing other stuff, and then I enjoy doing some other stuff, and then I do some other stuff. But a lot of people actually kind of like doing that. So let me tell you my favorite optimist, Sami Asaf, who is remarkable in her optimism, who once gave a talk at UCLA where the talk had a long abstract, but once she said, yeah, I'm almost done. Kronecker coefficients are going to be real soon. I can hear. That, I think, was Kronecker. Yes, you have. I have proofs. Sami, you're going to have, yes, I also have abstract to the talk. Sami, you're going to have your own 50 minutes. Let's, right after me, which was ingenious for the organizers of the conference. Thank you. And then Sami gave another talk, and that was Schubert. If you think I'm picking on Sami, you're wrong. You see there is a little box which says our bet. So let me tell you about our bet. Well, don't you want to know about our bet? Say yes. Okay. So after I was burned with the Kronecker experience, I wanted to put a timeline. What is the definition of real soon? And Sami told me a year and a half. So I suggested $1,000 and she rejected it. She said, let's do public humiliation. You're welcome. So again, not picking on Sami. The bet is a bet. So let me tell you now my reasons why I believe Kronecker coefficients would not exist. And the way I think of that is from a historical perspective. And I'm going to teach you history of mathematics. So everyone stay chill. And it's wonderful to teach history of mathematics to people who already know this is the history I'm going to teach. So you're going to learn absolutely nothing new. So I'm going to start with Pythagoras, who figured out that there are numbers which are not rational. And you have to understand it. It's hard for me to go into Pythagoras' mind, obviously, but that must have been revolutionary. This was so unusual and strange. It seemed not right. I'm sure people before believed it was. So there was a leap for a couple millennia, and Gauss showed that the heptagon cannot be constructed with a ruler and compass. You all know the story. I'm not going to tell you how it's done and what exactly he has done. But that is something really groundbreaking, that you can prove a negative result. People haven't been doing that for 2,000 years. And he did that. And after that, there was a lot of negative results. It just became a subject. People started to understand that lots of things that they wanted to do, like solve equations of fifth degree, that's just not going to work in the radicals. Okay? You all know the story. This is what we study in grad school or kindergarten, depending on your country. Liouville created this fantastic result, which is rarely taught actually even in graduate schools, about integrals being of certain elementary functions being not elementary. This laid the foundation for the whole differential algebra, and was a giant breakthrough. And let me tell you one more. Transcendental numbers. There is no reason to believe that they existed, except now we know they do. A posteriori, this is all obvious. And now all of this became revolutionary. Each of these 5 items, especially obviously the last few, gave rise to differential algebra, differential Galois theory became a large subject of differential algebra. We have an emergence of set theory, which later led to undecidability, modern logic. It became just a large subject coming from negative results. So and each of them, people believed for decades, for centuries, that it's impossible. Okay? People believe. Just like they believe that there are combinatorial interpretations for Kronecker coefficient. That's my point. Okay. Now that I dwelled on it enough, let me be more specific. So why would Kronecker coefficient not have a combinatorial interpretation? Somebody asked Greta this question, and Greta is like, "Yeah, Igor will do this," and I will. So the way I want to think about it is I want to think an imaginary conversation by Gauss and an anonymous friend when they're both 15. So imagine there is a gymnasium or whatever it was called back in Germany, and here is a picture of young Gauss, which was not dated, so I couldn't figure out if he's 10 or 20. Let's just assume he's 15, and he's having the following conversation, and just like chill and listen to the conversation. I'm going to render it in my best German. Why do you believe that the heptagon cannot be constructed? Asks a friend. And that's a good question. So Gauss says, I don't know, because many smart people tried and failed. Why do you believe it can? And that's the right reply when people ask you, why do I believe Kronecker coefficients don't exist? You ask them, why do you believe they exist? And here's what the friend says. Isn't it obvious? We can construct so much. We can do triangle, square, pentagon, octagon. That's just way too much. Heptagon is the only thing that's missing. I'm sure we're going to do it. Like tomorrow, maybe the day after tomorrow, but it's coming. That's my point. You hear that? Okay. So that is, I don't think that conversation happened, but it could have. And you know how I know it could have? Because when he was 19, Gauss proved the result. That's just 4 years. Between him, I don't know, to him, I do know. Okay, so now second part of the talk. What is a combinatorial interpretation? And I promise it's going to be just as fun. So the answer is that people give is basically anything that we can count. If you can count something, that's a combinatorial interpretation, and that's just wrong. Okay, let me explain that. And the way I'm going to explain it is by appealing to my book of my website, which has all the quotes of what is combinatorics. And there is this wonderful quote by Vanya Cherednik that who says that combinatorics is about counting of various things, which, for example, atoms, pebbles, and clusters. Okay, that's as good definition as any. And I have about 100 on my page, maybe 200. So here is my combinatorial interpretation for Kronecker coefficient. That's a whole pile of pebbles. To be precise, exactly G of lambda mu pebbles. Is that a combinatorial interpretation? Don't answer. Don't answer. Just think about it. If you believe it is, this maybe is not going to be educational. But if you believe it's not, try to figure out why it's not. Is that the pebbles? That's what it is, right? You don't like the pebbles. Cherednik likes pebbles, you don't. Well, that's fine. Let's do clusters. So here is a picture of star clusters. Is that good? Is that okay? Is that a good combinatorial interpretation? Yes? Don't answer. Just think it through. Is either of them better than the other one? Yes? You really, I know you want to say no, but you don't know why. So here is everyone good? So let me go to more math. So before I give a talk, I Google. And here is something I learned that happened during pandemic that I didn't know. Sarah Billy gave a talk. And she said that the Schubert coefficient problem has been solved. I didn't know that. I don't read arXiv every day. Some of you do, I don't. So you know what you do when you discover you don't know something? You email. So I emailed to Sarah. How did, what happened? Did she really, did you really solve Schubert coefficients problem? And she's like, well, we don't need to solve it. They already count something. They already count number of points in the intersection of 3 Schubert varieties. And now think that through. Is this better than pebbles or not? Yes? Why? Is that a combination? Because Richard Stanley knew that. He wrote in his original paper, these are the numbers, and I want a combinatorial interpretation. Are you currently saying that Richard Stanley is going to disagree with Sarah Billy?
I didn't say it's a combinatorial interpretation. I said that it's better.
Oh, it's better. Yeah, okay. But I personally think star clusters are better than pebbles, so that's not a low bar. So don't answer that. I'll tell you later. But think it through. Is that a combinatorial interpretation or not? And if it's not, you should really have a good answer why not. And if it is, we're done with Schubert problem. I don't know if Alan is smiling through his mask, but maybe hopefully he is. So here is another wrong answer. This is an answer from people who know Supreme Court history. And it's a good answer. It's a good answer. Mathematics is an art. I can tell you stories about that. So we don't have to define everything, but it would be nice if we did. And the reason it would be nice if we did is Karl Popper, who said that a belief needs to be disprovable in order to be scientific. So if you're not going to define what's a combinatorial interpretation, how can I, with all my negative attitude, say that you're wrong, that there is no combinatorial interpretation? We need a definition. We need something very, very formal that we can just take and say, look, if this is your definition, you're just wasting your time. Okay? And now I'm prepared to do that. So here is the correct answer. What's a combinatorial interpretation is Sharpie. I'll explain what it means in a minute. But let me, it's a very short answer, just 2 symbols. Okay, just 2, but a lot of meaning in that. And it took me years to basically sort of mentally prepare myself that there is nothing better. I grew up in Algebraic Combinatorics community. I always thought that there should be some tableaus, integer points, and polytope should be something better. Sharpie is just way too vague of a class. This are all these computational complexity people. We can do better, and the answer is no. So, like all these questions, like what is time, and what is space, those are deep questions. The answer to those questions change as we grow. In the beginning, we think it's all our room, and it's our village or something, our Earth. And then we realize space is bigger, has star clusters. You see what I mean? So in the same way, it's time. It was time for me to grow up, and that's what happened. So now I can tell you what is Sharpie. And Greta did some of that, and I'm going to do it again, and in a different way, and possibly worse. So I'm not actually going to define anything, but I will remind you of things you already know. So, P and FP stands for things you can do in polynomial time. P is the decision problems, FP is computing. Okay, we're not going to use FP much, but for the purpose of this talk, it's very important to understand that if you have a graph, you can decide whether it's connected or not in polynomial time. It's actually really easy to do. That's what we teach in the introductory algorithms classes. It's not so easy, but you can decide whether a graph has a perfect matching in polynomial time. That's a beautiful theorem. It's even less easy, but you can decide using this saturation theorem that Littlewood-Richardson coefficients are positive in polynomial time. You can do that. That doesn't mean you can compute them in polynomial time, but there are things you can compute. For example, you can compute number of spanning trees. Rick Kenyon mentioned number of perfect matchings in planar graphs. Those are using Castellan formula. Those are the things you can compute in polynomial time. You with me? And you can, and just for algebraic combinatorics lovers, you can compute dimensions of symmetric group, irreducible representations of GLN. You can do all of that, okay? Because determinants are powerful things, not very obvious. And you can do all that. So what's NP? NP is a class of problems where the objects can be verified in polynomial time. So when you're deciding whether a graph has a recoloring, so for you see it's recoloring on the bottom right, you can just look at every edge and check that the colors along that edge are distinct. Okay, that's what we would call proper recoloring. Everyone clear about this? So you can decide if a cycle which somebody alleges is Hamiltonian is actually Hamiltonian cycle. You can decide that on polynomial time. It's going to be hard for you to decide if a graph has a polynomial, has a Hamiltonian cycle, but verifying if somebody shows you Hamiltonian cycle, you can just verify it very, very quickly. And NP complete problems are problems that are complete in the class NP. Okay, so in other words, they are equivalent up to polynomial time reduction, to recoloring, to Hamiltonian cycle. Those are all NP complete problems. Any questions about any of that? Please don't. Just read Wikipedia if you do. So Sharpie. Sharpie is the ones that people know less, and this is the subject of the talk. This is a class of counting problems where the objects can be verified in polynomial time. So just like decision problem of having Hamiltonian cycle is NP complete, counting the number of Hamiltonian cycles in graph is a Sharpie complete. But the great thing about Sharpie is that we already have objects to verify. That is what we want to think as a combinatorial interpretation. Okay? That's why the definition is here. Because for all these problems, we have a combinatorial interpretation. The reason I have Littlewood-Richardson in the corner saying that it's Sharpie complete is because the Littlewood-Richardson coefficient counts something. They count Littlewood-Richardson tableaus, which is amazing because Littlewood-Richardson rule is amazing. And the reason we don't have the same result for Kronecker coefficients, because we don't have a combinatorial interpretation for Kronecker coefficients. So that is the point I want to make. It's the same problem, but algebraic combinatorials don't exactly like that. But in complexity, if you talk to people in complexity theory, they think it's an axiom. There is nothing else. Combinatorial interpretation is Sharpie. Okay? So where are we? Yeah. To verify if it works. So you're looking at Littlewood-Richardson tableau. Somebody says you, oh, here is tableau, it's Littlewood-Richardson. Then you check that it is increasing in rows and columns and so forth. And yeah, that takes polynomial time.
So if you have so many of those objects, that's not, well, that's still okay.
It doesn't matter how many you have.
Okay.
Just like number of Hamiltonian cycles is usually exponential. Or number of three colorings is almost surely exponential for most graphs. But sometimes it's not, but usually is. But verifying that each individual is there can be done in polynomial time. Everyone okay with that? You don't have to.
So the usual definition of Sharpie doesn't require it to be a counting problem. So it could be a formula which has lots of subtractions in it. So you would still consider this a combinatorial interpretation. Like a ratio of 2.
That is not correct. So the question is, can Sharpie has negative sign? And the answer is no. So you should be able to, verification process can be whatever you want. But the objects that you're counting have to be positive objects, and it will appear right on the next slide when you have negative.
Yeah, I understand. So you want a verification problem. You don't want a problem of computing some number.
You're counting objects. Think of objects being 0-1 strings. You're counting some 0-1 strings. Let me just finish. You're counting 0-1 strings, and somebody and you're saying that those 0-1 strings are in your class. And you should be able to verify if this 0-1 string is the one that you want in polynomial time. And your algorithm to verify can have determinants, can have weird stuff. Doesn't matter. As long as it's in polynomial time, it works for you.
That's not what I was asking. I'm asking about general Sharpie problems which may not relate to counting elements of a set.
Then you're wrong.
You require that.
Sergey, with all due respect, you're wrong. That's what the talk is about. Everything here is positive. Sergey is saying that I'm wrong, and I'm saying he is wrong. I think that's a short version.
Igor, it sounds to me you're casting Sharpie as a decision question. Is this a little?
No, it's not a decision. It's a.
We just cast it at that. It's a little. This is a color tableau. That's a yes or no problem, and that's empty as opposed to.
No. Sharpie is a class of counting. Are you talking to him or to me? I'm not. Sharpie is not about decision problems. Sharpie is a class of counting problems.
Yes, but
that's what it's.
Tableau, Littlewood-Richardson tableau is not a counting problem. That's a decision problem.
Right? You want the number.
You want the number.
Yeah.
You don't want to see whether an individual one.
No. You do. You're counting objects so that where each individual can be verified in polynomial time. So let me repeat again. There is clearly a lot of misunderstanding in the room, and I can hear it. There is like a heavy weight of that. Why is Hamiltonian cycle in Sharpie? Why is the problem of counting the number of Hamiltonian cycles? You have a graph. You're counting the number of Hamiltonian cycles. Each Hamiltonian cycle, deciding whether this object that you're counting is Hamiltonian cycle, can be done in polynomial time. The problem of counting the number of Hamiltonian cycle is Sharpie. That's the definition. So you can substitute general. Please let's not go through this again. Are you want to comment or answer a question? Okay, Perry, I understand that you want to contribute. Let's not do that. So we're counting objects. We're counting objects, and each object can be verified yes or no in polynomial time. I see your hand. Let's just move on. I'm sorry. Let's move on. So here is an issue. Sometimes sometimes the numbers that you want to have a combinatorial interpretation for are non-negative numbers and given as a difference of two Sharpie functions. Okay, that's called gap P, not Sharpie. That's gap P. That's a different class, and that's what we're doing. So turns out that this is the right class for the problem that we're working on. Kronecker coefficients, computing Kronecker coefficient lies in gap P. That's not Sharpie, Sergey. Gap P. I'm going to repeat it twice more. So the problem of computing plethysm coefficients, it turns out to be in gap P greater or equal to 0, which means it's a non-negative and it's a difference of two Sharpie functions. Again, Sergey, computing the Schubert coefficient turns out to be a difference of two Sharpie functions. It's non-negative and a difference of two Sharpie functions. It's very, very close to Sharpie, but it's a difference of two. If you're happy with a combinatorial interpretation of the Murnagama-Nakayama rule type, number of these things minus number of that things, that's we're done. That already exists. Okay? Most people are not happy about that. That's why, especially when you heard Lauren's talk, she said many times, manifestly positive combinatorial interpretation. She was right. That's what we want. Because otherwise, how do you go about deciding all these asymptotics and vanishing problems if you have something positive minus something negative? Okay? You're not going to be able, yes? That's what the talk is. So the question is it known that gap P and Sharpie are different? And I'm just going to rephrase it as gap P greater or equal to 0. Because otherwise you can have negative functions. And the answer is yes, and that's what we proved. So now, before I do that, let me make a note. Let's go back to Sarah Billy's combinatorial interpretation for counting the number of points in the intersection of Schubert varieties. Yes, she did. Yeah, she did. She did it in writing. And I have talk slides. And I had a quote before. She believed that this is fine, that they already have a combinatorial interpretation. And I believe they don't, and that's a matter of opinion. Okay? There's no definition of, I'm giving a definition of combinatorial interpretation. They don't fit into my definition of a combinatorial interpretation. And the reason they do is because you can't really be counting objects where the verification is extremely complicated. And those intersection of Schubert varieties are extremely complicated. How are you going to count objects when you don't know what where verification, finding them and verification them is going to be extremely hard. Finding what objects you need to verify. I'm not going to say much more about Murphy's law. It's a variation on Murphy's universality theorem. But the way to think about it, it's as bad as any algebraic varieties can get. Yes, Sam on top. So Schubert. Yes, you're right. I apologize. This is not C lambda mu. This is C UVW. So the point is, I made a typo. Instead of C lambda mu, I should have written C U. Yeah. You're totally right, and I know what about. Yes, Zach.
So when you're talking about this non-uncertainty, I guess the point is, or one word interpretation would be, when you look at an actual instance of a geometry problem, you don't have a discrete set that that's what it's in.
Correct. Okay. I mean, but it's worse. If those were low degree algebraic varieties, you could imagine doing that, but they're not. They're very high degree varieties. So Zach said that because those are complex varieties, it's actually hard to know what you should be testing. They're not discrete objects by nature. It's not like a 0-1 strings. This is I'm sort of adopting his question, and that is completely correct. Okay, everyone good with this slide? Yes, David. I didn't, because I don't believe any of that. So the question is, can one use numerical analysis to say that this combinatorial interpretation is actually combinatorial interpretation, and I didn't use it at all because those are, as I said, can be horrendously complicated. So you may as well ask about general algebraic varieties and do anything you want, and no numerical analyst will, if you actually talk to them, will agree that this is something worth exploring. Basically, they do everything on a computer, and computer dies after in degree 20 or something. Oh, absolutely. I know some of your colleagues do. That's not, that's, I'm.
You also don't need to actually have the object to count points at intersection.
Yeah. So I would be very open and welcome. And in fact, I invite anyone to make a new bet. I love making bets, and I'm gonna put a real money on it. So if you believe that there are combinatorial interpretations, just stand by your beliefs. We'll sign the contract. Some of the organizer will witness it. We'll have an escrow account. I'm cool with any legalese. We'll make that happen. Just let me know after the talk. Don't do it right now. So if you believe this is workable, great. Yes, question. I just said that I don't want to talk about it. So the Murphy's law said that is a variation of Munoz's universality theorems, which says in this particular instance that triple intersection of Schubert cells can be as complicated algebraic variety as you want them to be. That's a short version of the answer. I agree with your point. So the objection is that Murphy's law are not talking about zero-dimension objects, and that is correct because all zero-dimension objects are the same. So there's nothing to talk about, and I agree with that. And I stand by my beliefs, and I'm truly welcome for you to try this one.
There's also a complexity result about zero-dimensional varieties. They are single exponential, which you broke the basis for, but
Frank, I want to finish my talk. I want to finish my talk in time. So let me just do that. And I agree with everything you said. You're correct. So here are, so one question one can ask is, are there any other interesting problems? So if we cannot solve the Kronecker, Schubert, plethystic, maybe we can solve easier problems and prove that they, problems in gap p greater or equal to 0, that they are not in Sharpie, which is, you see where I'm going with this. And the answer is yes, there are quite a few. So for example, you can take a poset and you can take number of linear extensions and subtract 1. That's a gap p function. It's great to, every poset has at least one linear extension. So that's greater or equal to 0. And by definition, those two are Sharpie functions that you're subtracting. So that lies in gap p greater or equal to 0. And so that was perhaps too easy. Here is another one. Let's take a graph. Let's take k matchings in the graph. So those are k tuples of edges which have no intersections over over vertices. So k disjoint tuples of edges. And then a famous theorem, really celebrated, has 1,000 citations, says that the sequence of mk is log concave. That is, mk of g square is greater or equal to mk plus 1 times mk minus 1. Okay, that's a beautiful result using beautiful linear algebra, and I strongly recommend that result. And now by definition, those two are Sharpie functions. Okay, they're counting something. One is counting pairs of k tuples, another one is counting pair of k plus 1, k plus tuple, and k minus 1 tuple. Okay, so the difference is greater or equal to 0. That's in gap p greater or equal to 0. Okay, by definition. Here is a third one. I just picked at random because I like the result. There is Grimm's inequality for the number of spanning trees in a graph, which says that the number of spanning trees is at most the ratio of 2m to the n minus 1 divided by n times n to the n minus 1 to the n minus 1. Again, proof using linear algebra, beautiful exercise. You may not have seen it. I recommend it. By definition, since you do have Grimmett theorem, that's in gap P greater or equal to 0 because it's the difference of two Sharpie functions. Okay, and in fact, the reason I brought it up is because any inequality can be turned into any combinatorial inequality of this kind can be turned into a gap P greater or equal to function. You see what I mean? So let me take a somewhat harder one, which was proved just recently. You take a graph and you can see the K forests. K forests are spanning forests with exactly K edges. Okay, so a terrific result by one of the many results by Deprasita Hukat says that this sequence is log concave. Okay, if it's log concave, therefore the difference is going to be in gap P greater or equal to 0. You see what I mean? You can do it with any combinatorial inequality. You just created a whole large class of gap P greater or equal to 0 functions. Now, 1 and 3 are really easy to show that they're in Sharpie. I'm not going to do it. It's an exercise for you to just try and check if you they're solved in our paper. But it's good not to read the paper first and just do these exercises as a sanity check. Now, function 2 is in Sharpie, but for a non-obvious reason. That does not follow from the original Hellman-Lieb proof. It follows by the Christian Ikenmeyer proof, who gave a combinatorial proof of this result. It's a beautiful thing. Okay, very short paper, strongly recommended. And on the other hand, whether function 4 is in Sharpie is, as far as I'm concerned, is a major open problem. Basically, I'm saying that we don't know if this inequality has a combinatorial proof. Okay, if it did, we would have probably found if it has a direct combinatorial proof, but we don't. We now have several proofs. You see them at the bottom, including a lengthy technical but purely linear algebra proof by myself and Swihong Chan. And that's still the question whether it's in Sharpie is still open. So now to the last question, can we prove anything at all? And the answer is yes, we can prove stuff. And I'll tell you how to do that. So this is a proposition, it's not even a theorem. If you remember the first slide, our paper has 82 pages. It has a lot of stuff. So this is what we can, and this is technical because computer scientists write it in a technical way, but we're saying that if gap P square is in Sharpie, then polynomial hierarchy collapses to the second level. And it's really easy to prove. I just don't want to give the proof because otherwise I would have to give a lot of background. And let me mention that gap P square is by definition part of gap P greater or equal to 0 because it's non-negative and is a difference of two Sharpie functions. Okay, so I'm saying, so let me explain what I'm saying because that's not kind of friendly written. The way to think about this, suppose I have two graphs, G and H, two graphs, unrelated graphs. I look at the number of three colorings in this one, subtract the number of three colorings in that one, square it. Okay, I claim that that square does not have a combinatorial interpretation unless something horribly wrong goes in computer science. Okay, so if you find a combinatorial interpretation of that, you just made the revolution in computer science and don't hope for that. Okay, that's not going to happen. So is this clear what I'm saying? Yeah, I just have a few minutes to go. So let me explain now what is this the bad stuff. So the bad stuff is saying that if you can solve long finite length formulas, you can do decision problem with any number of quantifiers just as fast as formulas with two quantifiers. That's what collapses the hierarchy means. Okay, don't expect to do that. This is strong assumption that P not equal to NP. Nobody's going to prove that anytime soon. Okay, but don't believe that happens. And if you don't believe that's going to happen, don't believe this squared function is going to have a combinatorial interpretation. It will not. Okay. So let me give you a proof idea. A proof idea is the following. Essentially, suppose you do have a, like, here is, it's almost philosophical. Suppose you do have a combinatorial interpretation for the square of the difference. Then you can have a witness for number of three colorings of this graph being not equal to the number of three colorings of that graph. You see? Number of three colorings is really hard to compute. Saying something intelligent about two unrelated, number of three colorings of two unrelated graphs should be really hard to do. Saying that they're not equal, have different number of, giving a witness for them to have a different number of three colorings should be unexpectedly powerful. So I know this sounds like a mouthful, but it's a little bit similar to saying that you should, having a witness for a graph to be not Hamiltonian or not three colorable. Okay, you don't expect that to happen. We don't have a proof of that. This Greta mentioned CoNP stuff in her talk. Let me not do that. But this is on the same level of complexity type of thing, type of point. Okay, I have a couple more slides where I actually want to show the kind of things we did which are more powerful. So, for example, we can do a lot of inequalities. Remember, I just taught you how to convert inequalities into questions about get p greater or equal to 0. For many of these inequalities, including a really technical proof of Karamata inequality, we can do that under different complexity assumptions. Some of our complexity assumptions are even stronger than, or actually quite a bit stronger than the one I showed you. But the point is, if even sort of basic inequalities like this Hadamard inequality is basically saying that the volume of a parallelepiped it maximizes when all the edges are orthogonal. That's what it says. And even that kind of thing is completely non-combinatorial. There is a reason the proof uses eigenvalues. It's not going to be able to, you should not be able to prove it in a combinatorially by just reshuffling monomials. That's not going to work. So the last short portion of the talk, I figured I should give you something to remember. And that something is going to be this Gestalt sequence that I really like. And the sequence, it's a nice integer sequence. You see it on the right. Sometimes it's a little, it's increases a lot. Sometimes it decreases a little. I don't know how to use a pointer, but it is integer because you can just write it explicitly what it is using binomial coefficients. The terms with I are going to cancel, and you can just conclude that it's a difference, that it's some alternating sum of binomials. And on the other hand, it's greater or equal to 0 because the norm of 3 plus or minus 4i is exactly equal to 5. Okay. So, and in fact, it's a square, but that's not super important. And you know, once you look at the sequence a little more closely, you recognize that it's the generating function is rational, and you can write it explicitly. And the question is, does the sequence have a combinatorial interpretation? It's just as good question as any other question. It's a actual integer sequence. There is nothing fancy about it. I don't have time to tell you disease story, but let me just say that we don't know. Complexity arguments don't work in this case because there could be something very, very special about 3 and 4. Okay, we just don't know. But what I do know is that if you generalize this to work for any f and g, so in this case, if f and g are 1 and 2, then you get the usual Gestalt sequence. And by the same argument as before, you're going to the generating function is going to be a rational function by the same argument with the norm. Okay, I know I'm becoming to go fast, but I want to get to the end of the talk. Now the reason I chose f and g, which is a strange letters for integers, is because I want them to be Sharpie functions. Okay, so think of f and g as the number of 3 colorings in some unrelated graphs. And the question would be the same. Does this AN have a combinatorial interpretation? And now you can see where I'm going. The answer is no. They do have a nice combinatorial interpretation for A1 and A2, but already for A3, they don't, for a technical reason related to another assumptions in computational complexity. But for A4, they don't have a combinatorial interpretation for the same reason I just told you with the square, because you see F minus G square in there. Boom. Therefore, A4 you should not expect a nice combinatorial interpretation for this sequence. There could be something still very special about the Gessel's original sequence. But if you want to, but for the whole class of generalized sequence is not going to be true. And I just stopped at 5. I didn't go further, but I'm assuming that they're actually not in Sharpie under the right assumptions for all n. Okay? And that's it. Thank you, everybody.
Okay, well, I think everybody will agree that was a very exciting talk. And now we have time for some questions. Yes.
Yeah. So
could you repeat the question, please?
So let me make a short version of the question. The point is, yes, the sequence can be computed in polynomial time, therefore they have a combinatorial interpretation. And that's not what Gessel meant when he wanted to do it. And if you look at my, I thought about it for quite a while, and I came up with a better definition of combinatorial interpretation in this particular case. If you look at my ICM survey, I explain it. It's basically, it would be nice to do it in log space, but explaining why would take me some time. I think the question is if you want to prove that Schubert constant are in Sharpie or are not. Are not. Well, first of all, I recommend reading our paper. Second, basically, it would be then natural to look at special instances of the Schubert problem where one can distill the numbers to be hard from our point of view. But that's a very short and complete answer, because if I knew how to do that, I would publish tomorrow. And I don't. Jim. No. So I think the question is there a relative notion of good or bad combinatorial proof and good or bad combinatorial interpretation? And for me, it's binary. It's either in Sharpie or not.
Yes.
Gap P greater or equal to 0. It's really close to Sharpie. It's like 1 inch away. It's just crossing that inch is not going to be possible, in my opinion. The question is, what's the smallest complexity class for Schubert's or Kronecker? Yeah, and that's the one I gave. Gap P greater or equal to 0. I cannot repeat. I didn't hear. I'm really sorry.
Have a parallel story, or remotely possible to have a parallel story in terms
So the question is there, so rather than go through combinatorial effort, can we do linear algebraic effort and have a parallel theory for that? And this is not a direction I want to work on. It is true, and that there are people who do, let's say, quantum complexity theory, which comes the closest to linear algebra stuff that you're asking. But the questions that we're looking for, essentially, Kronecker coefficients, the reasons, the fundamental inequality there is Kronecker coefficient greater or equal to 0. That's a very simple looking inequality. And the proof is Matschke's theorem. That's a theorem that we learn in section 2, maybe, or section 1 in Bruce's book. This is really a fundamental basic result. And the fact that we cannot do that is the same kind of fact that we cannot do all these Cauchy-Schwarz type inequalities that I talked about before. But I cannot prove it. This is all I can prove, and that's already, but essentially until our papers, there were no papers which talked about separation between these two classes, even conditional separation. So we're still trying to see how far this goes. I don't. The question is, do I know anything about cardinalistic polynomials? And the answer is no. I mean, I do know them, but not their polynomials. Or, I mean, whatever I know is not enough to give an answer. I think a lot.
Question.
The question is, what do I think about complexity of computing the characters? That's how, and so we're not, so we have a paper in the works with Greta. We're not ready to announce the results.
Anything else? Is there anything online?
I think there was a question.
Oh, there was one up there. Okay.
The question is, what makes linear algebraic proof different from combinatorial proofs? And the answer is Matschke's theorem. It's so basic and fundamental, people ignore it. But it's really remarkable if you think about it.
Yes.
I don't like this question I'm going to ask, but I can't come up with the answer.
Then maybe after the talk, don't embarrass yourself.
So, is there any celebrated semi-counting formula in combinatorics that you would allow is not part of the thesis that you're making? That people love it, that it's really something that is counting things, but it is not a Sharpie set.
Well, the Murnagama-Nakayama rule cannot be improved. It's not in Sharpie, it's in gap P, but it has to be because it has positive and negative terms, and sometimes characters are negative. So that's as good as you can get. Yeah, I'm good at this level.
Yes.
Go ahead. That is also correct. If the number, if you're looking for sequence like 2 to the 2 to the n, that does not have a combinatorial interpretation from, and that may be answering your question, but that's a pathetic sequence. Don't consider.
Anything else from the audience here? Okay. Vic, you said you had some online.
Yeah, there was just one comment earlier. Was the argument about what's Sharpie. The Wikipedia definition of Sharpie is the set of counting problems associated with the decision problems on set N.
That's what I said in a different way. Thank you, Nathan. Thank you for coming to Zoom talk and making comment.
Okay, well, I think we can thank